In this video, we're glad to share our work titled Neural Implicit Reconstruction and Fast Rendering based on Dual Spherical Shell, recently accepted by ICME 2025. SDF-based rendering typically follows the sphere tracing strategy. On the left, you can see the original method. At each step, the SDF value is computed to determine a conservative stepping distance. On the right is Nglad's improvement. It uses an octree structure to skip over non-surface regions through ray-cube intersection checks. Both approaches rely on globally or locally sequential ray stepping. While NGLOD accelerates stepping, all relevant surface grids are traversed in the sequential order. We propose the Dual Spherical Shell, DSS, representation, which extends two of our previous works. The upper part visualizes 32 inner key spheres across three models. To construct the DSS, each inner sphere is paired with a concentric outer sphere that shares the same center but has a larger radius. The space between these sphere pairs, referred to as interlayers, forms a shell that fully encloses the model's surface. For the beneath model, the number of concentric sphere pairs increases from 8 to 512 from left to right. As more sphere pairs are added, the DSS better conforms to the surface, and the interlayers become thinner. With DSS, we enable local SDF fitting. This 2D bunny example illustrates DSS constructed with 4 concentric spheres. SDF fitting and model reconstruction occur within the interlayers. To predict the SDF value, we encode the feature vector between a query point X and the sphere center C using positional encoding, concatenate it with the latent vector of the corresponding shell, and input it into an MLP. More importantly, DSS enables early termination and parallel sphere tracing for SDF rendering. In the left figure, the ray hits both concentric spheres, indicating the surface point lies within the highlighted red interval, enabling early termination. In the middle figure, the ray only intersects the outer sphere, resulting in multiple valid intervals that can be stepped through in parallel. Here, we present our experimental results for SDF reconstruction. On the left, the table summarizes average metrics on the Thingy 32 dataset. On the right, we visualize reconstruction results for two 3D models. Our method achieves a lower chamfer distance with significantly reduced storage requirements. The table here compares the rendering performance of different methods on two models. The average number of ray steps indicates stepping efficiency. Preparation time includes preprocessing like ray sphere or ray octree intersections. SDF query time is the duration spent querying the neural network. Step time reflects the cost of ray iteration, and is primarily proportional to the number of ray steps. We also integrated DSS into NUS to support local SDF fitting and uniform sampling within the Dual Spherical Shell. The images on the right show the novel view synthesis results. DSS not only captures finer details but also achieves significantly faster inference. In summary, the proposed Dual Spherical Shell is a novel 3D representation that addresses several key challenges. It offers high-fidelity reconstruction, improved memory and storage efficiency, accelerated rendering, and enhanced NUS synthesis. Thank you for watching. This work represents 2 years of effort, completed by 4 students and 2 supervisors.